Hi, this is Marc Roth, and this is Mathematics for Social Justice. Today's lessons will be on Quadratic Functions Mod 7. So today we're going to complete a chart for a function where these numbers here under x are the inputs, and these values under y will be the outputs of a function where your inputs are from the set of the numbers on this clock, mod 7, and the outputs are also on this clock, mod 7. And since 7 is a prime number, we'll be working with what's called a finite field. So the rules, basically, of the algebra will be pretty much unchanged from when you do other functions. So that aren't based on the clock, but are, say, based on the real number line. So we have to, first of all, fill in these other missing values. But that's possible because three values determine a quadratic function. To do that, we just may have to make sure that these second differences are constant. And this is the delta in the Greek alphabet, capital delta. It stands for the first differences. And we're not squaring them. Instead, the symbol will stand for the second differences. So basically, when I go 0 and 2 and subtract, I'll get negative 2, which is equal to positive 5. But now I can't do any more filling in of the chart yet. So to fill up in the rest of the chart, we're going to make use of Pascal's triangle. But before we do that, I'm just going to build a function using the help of three imaginary helpers. So I'm going to have a student named Kara help me, and a student named Nicole, and a student named Tom. So Kara picks a number. Suppose she picks 3. So that's the first output. So for the next output, Kara's number is used again, and now Nicole gets a number. Suppose she chooses 2. So after that, we still use Kara's number. Now we're going to use Nicole's numbers twice. And now we're going to use Tom's number for the first time. Tom chooses, let's say, 5. So next, we always use Kara's number. We're going to use Nicole's number 3 times now. And we're going to use Tom's number 3 times. So the question is, why 3? Well, it turns out the numbers in the coefficients in this column are going to be triangular numbers. So if you look at a triangle, 3, you can make a triangle with 3 dots. We also consider a single dot to be a triangle. So the next one would be 6 dots. So that would be the next number down would be 6. These numbers are getting bigger by 1 each time. So you can actually write it like this. And then we have 4 finally. And we always have one of these. So this would also be a 3 again. And we can put in plus signs. So we're building ourselves a quadratic function mod 7. So our first output would be 3. And then we would get 5. And then we would get 4 plus 3 is 7, which equals 0 plus 5 again. And then we're getting 3 plus 6, which is 9, minus 7 is 2. And this is 15 minus 14 is 1, and 2 plus 1 is 3. Then we're going to get 8, which is 1, plus 3 is 4. 4 plus 30. 30 is equal to 2, so 4 plus 2 is 6. And we just keep going like that. So the next, 1, 2, 3, 4, 5, we would need 2 more rows. So here we would get 10 for the next triangle number, but 10 minus 7 is 3. So this would be 10 plus 3, 13. 13 plus 15 is 28, so this would be 0. And we just need one more row. So when you add 5 and 3, well, actually, the next one would be 15. And 15 take away 14 is 1. So that'd be 1 times 5. So that would be 12 plus 3, 15, which is equal to 1, plus 5 is 6. Now let's look and see if we have anything that looks quadratic. So we have 0. Think of this as a loop of numbers, like a necklace. So we have 0 surrounded by 2 6s, surrounded by 2 3s, surrounded by 2 5s. And this is exactly what we wanted to get from a quadratic. But it turns out you may be able to recognize these numbers. So these numbers, especially like 1 3 6, we can find them in Pascal's triangle. So let's take a little detour and talk about Pascal's triangle. Pascal's triangle is usually written like this. So it's 1 on the left, 1 on the right, 1 on the left, 1 on the right, add 1 plus 1 and get 2. And it's 1 on the right, on the left, 1 on the right, 1 plus 2 is 3, 3. Next row, start on the left with 1, on the right with 1, add, get 4, 6, and 4. So we add 3 and 3 to get 6, 3 and 1 to get 4. So then add 1 on the left, 1 on the right, add again the two numbers above, 10, 10, 5. Now, let's focus on this number. This number is equal to 5, choose 2. Usually written like that. So what does that mean? That means if there's 5 things and you must choose 2, this is how many ways you can make that choice. So how do we account for that spot? We don't count this number as 1. This is actually considered the 0th row. We don't say 1 till we move down. So we go 1, 2, 3, 4, 5. Then we count in. Again, this is 0, 1, 2. So again, this is 1, 2, 3, 4, 5, 1, 2. So it's 5, choose 2. So 5, choose 2 is 10. We can verify that with the multiplication principle. So if you're going to be taking 2 things from 5, there's 5 things you can choose first, and 4 things remaining that you could choose second. But if you choose 2 things, you could have chosen one of them first and one of them second, or reverse that and choose the second one first and the first one second. So actually, if I go 5 times 4, I'm counting everything twice. So I have to divide by 2. So if I do that, 20 divided by 2 is 10. So that verifies that 5 choose 2 is 10. Now, instead of writing Pascal's triangle like this, sometimes it's convenient to change its shape. So we're going to write Pascal's triangle in left justified form. So it would be 1, 1, 1, 1, 2, 1. Again, I'm adding 1 plus 1 to get 2, 1 plus nothing to get 1. It's always 1 on this column. 1 plus 2 is 3, 2 plus 1 is 3, 1 plus nothing is 1. And then 1 plus 3 is 4, and then 6, and then 4, and then 1. But it turns out we don't need more than 3 columns for a quadratic. So we don't need these 2 columns. And it's convenient to add zeros here. So we get a rectangular block of numbers. And then it's convenient to add parentheses, plus signs, and equal signs. So we're going to get 1 parenthesis plus 0 parenthesis plus 0 parenthesis equals 1 parenthesis plus 1 parenthesis plus 0 parenthesis equals 1 parenthesis plus 2 parenthesis plus 1 parenthesis equals 1 parenthesis plus 3 parenthesis plus 3 parenthesis equals 1 parenthesis plus 4 parenthesis plus 6 parenthesis equals 1, 2, 3, 4, 5. 2 more rows is all I need. So 1 parenthesis plus 5 parenthesis plus, well, 4 plus 6 is 10, but that's equal to 3 mod 7. So we write 3 parenthesis equals, and 1 parenthesis plus 6 parenthesis. Now 5 plus 3 is 8, mod 7 is 1. Now, these numbers here kind of wrap around as a loop. So I can go and I can put 2 and 0 actually on the top. And then I go around, so it's 2, 0, blank, blank, 5. So it's 2, 0, blank, blank, 5. Now, remember we called this after Kara, so we'll use that again, C. Actually, it stands for the word constant. And this is going to be N. Actually, instead of being Nicole, it's natural numbers. And here, triangular numbers. So Tom was actually triangular numbers. And this coefficient is 0, and this coefficient is 0, so these two terms won't contribute to the 2. This has to be 2. But then it's 2 all the way down. It's like a turtle on top of a turtle on top of a turtle, etc. And now we can focus on this spot. This coefficient is 0, so this won't contribute. So 2 plus something is 0. 2 plus negative 2 is 0. And negative 2 equals positive 5 on the clock. So it's positive 5 all the way up and all the way down. Next, we're going to focus on this spot because we want to make 5. So that's 2 plus 20, that's 22. Now when you subtract 21, you get 21 is a multiple of 7. So we're subtracting 21 from 22, and we get 1. So 1 plus something is 5. 1 plus 4 is 5. So we want 6 times this number to be equal to 4. So let me write that as an algebra problem. 6 times something equal 4. So I can divide both sides by 6. That cancels. So x equals 4/6, which reduces to 2/3. So now I'm going to divide the bottom into the top. Now if 3 doesn't go evenly into 2, I can transform 2 into 9 by adding 7. Because I can do that on this clock. Then 3 goes into 9 3 times. So I believe this will be a 3. Let's double check. So that's 22 plus 18 is 40. Take away 40, take away 35 is indeed 5. So this 3 worked, and I can use 3 all the way up and all the way down. Okay, so at this point, I can finish these numbers. So I'm going to have 10 plus 2 is 12, plus 3 is 15, take away 14 is 1. And 15 plus 2 is 17, 17 plus 9 is 26. Subtract 21, 26 minus 21 is 5. So here I'm going to have 25 plus 2, 27, plus 9 is 36. Subtract 35, I get 1. Here I get 30 plus 2, 32, plus 3 is 35, which equals 0. Now let's see if it looks quadratic. So it looks like 2 is going to be surrounded by 2 zeros, 2 1s, and 2 5s. So it looks quadratic. So if we made a loop, it would be 2 surrounded by 2 zeros, and then surrounded by 2 1s, and then surrounded by 2 5s. So this is what a quadratic should look like. So we can go ahead and fill in this chart. So it's 2, 0, and then 1. And then looping around, we're going to have 2 5s, a 1, and a 0. So now, again, this delta stands for differences we'll be subtracting. So 2 minus 0 is 2. 0 minus 1 is negative 1. On this clock, it equals positive 6. 1 minus 5 is 4, negative 4, which equals positive 3. But I don't have to do any more work because this is supposed to be linear, which means the numbers get bigger or smaller by the same amount each time. They're getting either bigger by 3 or smaller by 4. So I should say bigger by 3, smaller by 4, bigger by 3, smaller by 4, bigger by 3, smaller by 4. And I should have every number one time. So I have 0, 1, 2, 3, 4, 5, and 6. So now when I subtract, 5 minus 2 is 3. Negative 4 is also 3. These should all be 3's. 3 minus 0 is 3. So now I'm going to take the top numbers, 5 and 0 and 3. And I call this number C, N, and T. And we can use those numbers to build a quadratic. The only problem is most schools don't use C, N, and T. Most textbooks don't use C, N, and T. They use other letters. As a matter of fact, C, N, and T are just my own invention. I don't know if anybody else uses those letters. Most people use A, B, and C. So they get, when I was introduced to quadratics a long time ago, the introduction was just ax squared plus bx plus c. So I didn't hear anything about these second differences when I first learned algebra. Well, I'll leave the derivation to the listener, but it's not that hard to derive that a equals half of t. Okay, and that b equals n minus half of t. So what's half of t? Half of t is half of 3. We can change 3 to 10 by adding 7. So half of 10 is 5. So we get 5x squared. Now to get b, it's n minus half of t. So it's 0 minus 5. Half of 10, remember, is 5. So 0 minus 5, negative 5. Negative 5 equals positive 2. And then finally we get c, and c is 5. So it's the same two c's. This c and this c are the same c's. So we get 5. That means if I were to plug in 4 into this equation, the output should be 2. So let's double check that. If that's 5 times 4 squared plus 2 times 4 plus 5, let's simplify this and make sure that when 4 is the input, the 2 is the output. So here I get 16, and 16 take away 14 is 2. So this is equal to 5 times 2, 2 times 4, plus 5. So that's 10, minus 7 is 3, and that's 8, minus 7 is 1, and that's 5. So add these up, you get 9, and subtract 7, you get 2. So when the input was 4, the output was 2. Okay, let's try one more. Let's see what happens when the input is 6 and see that the output is 1. So we're going to have 5 times 6 squared plus 2 times 6 plus 5. So that's 36. Take away 35 is 1. That's 5 times 1. That's 5. 12 take away 7 is also 5. So 5 plus 5 plus 5 is 15. Take away 14 is 1. So when 6 is the input, 1 is the output. And we were able to complete this chart with the help of Pascal's triangle and our Mod 7 clock. Thank you.